Welcome to the series on analysis of 1D element using FEM. In previous lectures, we have discussed about the theory related to 1D element and assembly of 1D elements. In the last lecture, we have solved one problem related to the spring element. In this video, we are going to solve one more problem which is related to bar element. So let us start. A stepped bimetallic bar made up of aluminum having Young modulus E is equal to 70 to 10 raised to 3 Newton per millimeter square and steel having Young modulus of 200 into 10 raised to 3 Newton per millimeter square is subjected to an axial force of 5000 Newton as shown in figure. It is attached to a rigid wall at node 1 using FEM. Determine nodal displacements and reaction force at the support. This is the figure which is given in the problem. So let us write the given data. So we are considering aluminum as element number 1 and steel as element number 2. So length of element 1 L1 is equal to 100 mm. Length of element 2 that is steel is equal to 100 mm. A1 area of the element 1 is 100 millimeter square. Area of the element 2 is equal to 70 millimeter square. Young modulus for aluminum 70 into 10 raised to 3 Newton per millimeter square. Young modulus for steel is 100 into 10 raised to 3 Newton per millimeter square. F3 force acting at node 3 is 5000 Newton acting towards left, and U1 displacement at node 1 is equal to 0 since it is attached to the rigid wall. Now let us draw a discretization diagram. So after removal of the rigid wall, we have reaction at node 1 which is acting towards right opposite to the force acting at node 3. L1 is a length of element 1. L2 is the length of element 2. U1 is the displacement at node 1. U2 is the displacement at node 2. U3 is the displacement at node 3. A1, E1 that is area and Young modulus respective to element 1 are denoted by A1, E1 and area and Young modulus related to element 2 are denoted by A2 and E2. Let us write element connectivity table. So for element 1, we have local node as 1, local node number 1 as 1 and local node number 2 as 2. Okay, for element number 2, we have local node number 1 as 2 and local node number 2 as 3. As you might be remembering, these are nothing but the global node numbers in the system marked for each element. Whereas for individual element, when we consider local node numbers will be always 1 and 2. So now let us compute the total degree of freedom of the system. So we calculate the total degree of freedom of the system as DOF per node multiplied by total number of nodes. Since this is a one-dimensional system, we have DOF per node as 1 and total number of nodes in the system are 3. So therefore, the total degree of freedom of the system is 3 and therefore the dimensions of global or composite stiffness matrix will be 3 by 3. So let us compute element stiffness matrix. So for element 1, we have K1 is equal to A1 E1 upon L1 into matrix of 1 minus 1 minus 1 1. So for element 1, we have area is equal to 100 mm square and Young modulus has 7 into 10 raised to 3 Newton per millimeter square. And length of the element 1 is 100. So if we substitute, we have 100 into 7 into 10 raised to 3 by 100 into the matrix of 1 minus 1 minus 1 1. So if we simplify, we get 70 into 10 is 3 into the matrix of 1 minus 1 minus 1 1. Similarly, for element 2, the element stiffness matrix K2 will be equal to A2 E2 by L2 into matrix of 1 minus 1 minus 1 1. So A2 that is area for element 2 is 70. E2 Young modulus for element 2 is 200 into 10 to 3 and length of element 2 is 100. So therefore we have A2 E2 by L2 as 70 into 200 into 10 to 3 by 100 into the matrix of 1 minus 1 minus 1 1. If we simplify and take 70 into 10 to 3 as common, we have 2 minus 2 minus 2 2 as the matrix. And let us mark the global node numbers related to each column as well as row. So for element 1, we have global node numbers 1 and 2. Therefore, columns will be numbered as 1 and 2. Similarly, the rows will be numbered as 1 and 2. For element 2, we have global node numbers as 2, 3. So columns as well as rows will be numbered as 2 and 3. Now let us compute the global stiffness matrix, which is the summation of element stiffness matrix for element 1 and element stiffness matrix for element 2. So let us compute this matrix as we have used a trick in the previous lectures. So since the size of a global stiffness matrix is 3 by 3. Let us mark 3 columns and 3 rows. Now to write each and every element, we have to refer for the column numbers and row numbers. So for the first element of the first row of global stiffness matrix, we have to look for the column number 1 and row number 1. So that will have in element 1. So column number 1 and row number 1 will give us value 1. So first element will be 1. Second element will be column number 2 and row number 1 that will have in element 1. So column number 2 and row number 1 will give us the value minus 1. So second element will be minus 1. Third element will be column number 3, row number 1. We have column number 3 in element 2, but we do not have corresponding row number 1. Okay, so therefore the element value will be 0. Now for the second row first element, we have to look for column number 1 and row number 2. So that will have in element 1. So column number 1 and row number 2 will give us value minus 1. Now for column number 2 and row number 2, we have to look for both elements. Okay, so in element 1, we have column number 2 and row number 2 gives a value 1. Whereas in element number 2, it gives us value 2. So 2 plus 1 will be the value of the second element of second row of global stiffness matrix. Now for the third element, we have to look for the column number 3 and row number 2. So column number 3 and row number 2 will give us the value minus 2. So therefore, the third element of second row of global stiffness matrix will be minus 2. Now for the third row, first element will be column number 1 and row number 3. So we don't have that. So we'll have the element value equal to 0. For the second value of row number 3, second element value of row number 3, we have to look for column number 2 and row number 3. So that will have in element 2. So column number 2 and row number 3 will give us value minus 2. So therefore we have written minus 2. And the last element we have to look for the column number 3 and row number 3. That again will have in element number 2. Okay, so column number 3 and row number 3 will give us the value 2. So that is why we have written value 2. So in this way, we compute the composite stiffness matrix. So therefore, the final stiffness matrix will be K is equal to 17 to 10 to 3, 1 minus 1 0, minus 1 3 minus 2, and 0 minus 2 2. Now let us mark the column numbers as well as the row numbers. Okay, 1 2 3 and 1 2 3. Now let us write a global load and global displacement vector un. So global force vector will be the matrix of the forces acting at each node, isn't it? So of the system. So we have F1, F2, F3. Okay. For F1, that is node number 1, we have the force acting at node number 1 will be R1, isn't it? That is acting towards right, so therefore positive. At node number 2, we do not have any force, so therefore we have value 0. And at node number 3, we have the force F3 acting towards left. So as per the sign convention, we have it a minus. Okay, and the magnitude is given as 5000 Newton. Okay, similarly, we can write the displacement vector. So global displacement vector is the matrix of the displacements acting at each node of the system, isn't it? So for node 1, at node 1 we have displacement u1, at node 2 we have displacement u2, and at node 3 we have displacement u3. So therefore, global displacement vector will be matrix of u1, u2, and u3. Now let us write the global relationship, which is equal to K into Un, that is equal to global force vector F. So let us write the global stiffness matrix, global displacement vector, and force vector, which we have written previously. Okay. So we have 17 to 10 is to 3 into matrix of 1 minus 1 0 minus 1 3 minus 2 and 0 minus 2 2 into the global displacement matrix U1 U2 U3 that is equal to the global force matrix R1 0 minus 5000. Let us mark the column numbers and row numbers. Okay, 1 2 3 1 2 3. Let us consider this equation as equation number 1. Now let us compute the nodal displacements. Now at node 1, since there is a fixed support, the displacement at node 1, that is U1 will be equal to 0. Now using Gauss elimination method or approach, we delete the rows and columns from global stiffness matrix related to node number 1 and we delete rows related to node number 1 from global load vector as well as global displacement vector. So therefore, after elimination, we'll have 17 to 10 is to 3 into the matrix of 3 minus 2 minus 2 2 into the displacement U2 U3 that is equal to the matrix of 0 and 5000. So from this we can write 17 to 10 is to 3 into 3 into U2 minus 2 into U3 that will be equal to 0. And second equation will be 17 to 10 is to 3 into minus 2 U2 plus 2 into U3 that is equal to minus 5000. So after solving these two equations, we have the displacement at node 2 that is U2 is equal to minus 0.0714 mm and U3 equal to minus 0.10714 mm. Now let us compute the reaction at support. So from equation 1, we have this is equation number 1. So from equation 1, what we can write 17 to 10 is to 3 into 1 into u1, okay, minus 1 into u2 plus 0 into u3. Now since u1 is equal to 0, we'll have first value here in bracket as 0, then minus 1 into u2. So that is what we have written. And third is u3 is 0. Okay. So 0 minus u2 that is equal to r1. So let us substitute the values of value of u2. So 70 to 10 is to 3 into 0 minus then minus 0.07142 that is equal to R1. Okay. So when we solve, we get the value of R1 that is reaction at node 1 is equal to 5000 Newton. The positive sign indicates that the reaction acts towards the right. So now let us consider the problem given. So if we write Fx is equal to 0, that will give us R1 is equal to F, isn't it? That must be equal and opposite to the external force acting at the node 3. And therefore, as you can see, R1 which we have computed that is equal to and opposite to force, external force acting at node 3. Our problem solution is correct. So thank you for watching. If you like the video, please like, share and subscribe.